Thanks for attending the Shardy sessions. Yeah, I can only just present remotely on behalf of the whole team. Yeah, Shardy is just a unified partitioning system for the Alphabet and the external customers. Yeah, it's my great honor to present this project on behalf of the whole team. We have many contributors, of course, Google DeepMind and XLA in both London and Montreal. So it's just it's a project of course different time zones and of course different teams. In today, first of all, we'd like to just announce the great news that the Sharding JAX will be just, you can now just try the Sharding JAX with this config. Currently this flag, this config was false. You can just enable this flag and experience the JAX, experience the Sharding JAX directly. And this flag will be just flipped to the true very soon. We expect to just enable this Sharding JAX at the very beginning of the July. And we also provide this collab tutorial, which is a great starting point for all users with whether or not you are familiar with the SPM system. So in today's presentation, I will just have an overview of the whole partitioning system. Afterwards, we'll dive into specific components in the Sharding. First of all, it's just the history of this partitioning systems. At Google, there are two primary partitioning systems. The first one is maintained by the XLA, which is a GSBMD. We partition the whole computation into several. We annotated operations instructions with the Sharding annotations, and then partition instructions and insert corresponding collective operations. And the other one is maintained by the DeepMind model scaling team, which is the PodIR, which is another dialect just handling the SPMD system and MPMD systems for the partitioning. We noticed that there are just potential issues, especially, for example, which may trigger the confusion for the users on this which partitioning to use. Also, we noticed that there are this duplication of the effort and duplication of the experience on that. After DeepMind merged into Google in April 2023, the two teams found a common ground for the collaboration. And then we just decided to make a unified partitioner, which is the Sharding. We target to just define a unified representations and API and combine the best features from both systems. For example, the access-based shardings and the propagation schedule in the JSMD. We also just leverage the learnings from both teams and migrate the users in both worlds into the unified one. In the Sharding, we also just provide more enhanced user control and debuggability, as well as the compatibility with OpenXLA and JAX by using the MLR dialect. So with Shardy, users can just enjoy several benefits. First of all is that the broader set of active contributors. We have contributors across different time zones, which can help us to have a very quick response and feedback for our users. Also, by merging the two, by providing unified APIs and leveraging the experience from the two worlds, we try to find the common essence in the two code bases and extract and simplify and extract the common ones. So the new code base is much simpler than the previous either PodIR or JSBMD. Also, we have noticed the potential performance improvements, especially with the new features of the explicit reshards and the reshard collectors. We'll dive into them at the in the next sections. Also, we have a tighter JAX integration such that users can experience this sharding with the JAX directly with config. And we provide much more controllable and predictable for users as shown in this philosophy. Compared with JS3D, the Shardy just has enhanced the basic strategy and reduced the heuristic methods and provide much more controls for users. With Shardy, users can experience the active development compared with the passive development in the JS3D. Further, we just simplify the corresponding APIs and sharding strategies to provide much more controls for users. And these tools are just fully public, and we provide visualization and debuggability tools to help the users to visualize this process. This is overview of the SPMD system. There are three key components, critical components in the SPMD system. The first one is sharding representation and APIs. It's the interface and the protocol we provide. Users can leverage them communicate with our functionalities. The second component is the sharding propagation. The users doesn't have to annotate shardings for all the operations in the communication graph. Users really just annotate the shardings for several key operations, for example, for the input and output. Also, define several shardings, annotated shardings for several key tensors in the communication graph. The sharding propagation will just propagate shardings throughout the graph, such that each tensor can get the shardings inferred from both operands and results. The third component is partitioner, which will apply both the annotated shardings and the propagated shardings into the communication graph. We have this path is a transformation from the global shape to the local shape. We also just insert the necessary collective operations accordingly. For example, we need to insert the reshard operations, which is we are just translated into the specific collective operations such as altogether, all-to-all. The first two components are fully available in Shardy, and the third components we have a simple version which will be online quickly. In the next three sections, we'll just dive into each of them in much more details. So first of all, let's dive into the sharding representations. Sharding, as in the background, I'd like to just have an introduction to the mesh axis and the sharding representations based on this mesh axis. Mesh are just the shape of this device clusters. For example, in this example, we have the 2x2 device clusters, and we reshape them into 2x2 device arrays, as shown in the graph on the lower left. And then we can apply, when we just apply shardings to the specific tensor, we map the corresponding tensor blocks into the specific device. For example, if in the first example, we do not partition the tensor, such that each device will have a full copy of the tensor. In the second example, we partition the first dimension along the axis x, which means that we partition the tensor along the first dimension, and then send each partition, distribute the shard into the corresponding devices, such that device 0 will get the first partition A and B, device 1 will share the same copy as device 0. Similarly, if we partition the second dimension along Y, we'll just partition the tensor along the second dimension. And then the first device will get the data blocks A and C. We can also combine these two shardings together, partition the first dimension along X and partition the second dimension along Y. And then each device will get a quarter of the whole of the original tensor. Yeah, with that background, we can dive into sharding implementations here. Sharding is just an attribute of the operation which defines how we partition the results of this operation. Yeah, in this example, we have a match of 2 by 4 by 2 by 2, which corresponding to the total number of devices of 32. We have 32 devices and reshape them into this mesh. And then we partition the first dimension along W and X, and we do not partition the second dimension, which means the second dimension is fully replicated. And this Y and Z are not used to partition this tensor, which implies that the tensor is replicated along Y and Z. With Shardy, we just provide a much more intuitive representations than the original HL sharding and the GSBMD sharding. As shown in this figure, with Shardy, since the sharding representations is now rely on this mesh axis, it's much more clear that to notice the difference between these two shardings. It's easier to find that the only difference between these two shardings is that the sharding 2 has an extra sharding axis X along the first dimension. However, as a comparison, it's very difficult for us to visualize this difference in the HL sharding in both V1 and V2. And this advantage helps us to simplify our implementation and to mitigate several issues in the original GSBMD system, since it's much easier for us to handle this axis instead of this device array and so on. So we also provide much more fine-grained control for the users to annotate shardings. This slide just introduce the users can specify the source and the target sharding axis by using this explicit or this implicit replicated axis, which is the source of the sharding propagation. Only the implicit replicated axis can be used to further partition tensor. If an axis is explicitly replicated, we will not use it to further partition tensor. Also, if a dimension is closed, which means that this dimension will not get modified in this propagation, we fully respect users' annotations. Another powerful tool is the user priorities. Since sometimes we in the JSPD we just using several heuristic methods to resolve the conflicts, and it's very difficult for us to just demonstrate this philosophy, demonstrate the functionality to the users. Now users can use this priority to specify the propagation schedule on their end. For example, in this example, it's just two addition, and we have a conflict along this in this propagation. We can either propagate in this example we have we can either propagate the x from add 0 to the add 0, or we can either propagate the y from add 1 to the add 0. Since this is the addition is just is very simple element-wise operation, we can either propagate the x or y to the add 0. In the JSPD system, we have the heuristic methods to define to decide the result sharding of the add 0. But with the user priorities, user can define the priorities for each axis. For example, if the add 0 has the higher priority, we ensure that we propagate y first to the add 0. And then since the add 0 has already the partition along has already partitioned by the y along the first dimension will not further partition it along x. And this property is super powerful when handling for users to handle several propagation schedule. A typical example is that we'd like to handle the batch parallelism or the state parallelism at first, and then with maximum shardings, and finally with the zero memory, and finally with the zero memory optimizations. Finally, is that we have visualized the sharding propagation process with the sharding rules. The sharding rules is just how we reflect the relationship of these dimensions. I think a typical example is for the dot operation. Here is just the standard dot operation with the batch dimensions, with non-contracting dimensions and the contracting dimensions. The sharding rules for dot operation is similar to its ISO notations, and we also define the reduction dimension, which is k, which means that if we partition the reduction dimensions, we'll need to insert the or reduce scatter at the end of this dot operation. A complicated for the reshape is we also define the compound factors for the reshape. In this example, we reshape the tensors from 8x4 to 2x16, and it has the shape merging and shape splitting and shape merging. We define the compound factors to visualize this process. And the other part, the propagation and the partitioning part, will heavily depend on the sharding rules to decide the result shardings and the collective operations we insert. In the sharding, we propagate shardings along three directions, along all dimensions, both forward directions, backward directions, and sideways directions. Sideways directions means that we propagate shardings between operands and between results. So the second component is the propagation algorithm. Here we just have the simplified version to go through the dot operation. In general, there are just three steps. The first one is projection. The first step is to project shardings from dimension space into the factor space. And second step is to propagate shardings in the factor space. Finally, we project shardings from the factor space to the sharding space. And these two spaces are connected by sharding rules discussed above. We're just taking the dot as an example to go through this section. This dot is just a very simple dot. We just have there are just one LHS, it's just one. We have one LHS non-contract dimensions, RHS non-contract dimensions, and one contract dimensions. Here we first define its sharding rules. It's similar to its ISO notations. And the first step is we project shardings from dimension space to the factor space, and we fill out this table. Here, the LHS has the sharding batch and tensor. Batch is along the first dimension, and the tensor is along second dimension. We fill out this table. Batch is partitioned LHS along the factor I, and tensor is used to partition LHS along factor K. And RHS and dot doesn't have any shardings. It's fully replicated, such that these entries are just empty. And the second step is to propagate shardings along the factors. In this table, we propagate shardings along each factors. For example, we propagate the batch axis along the factor I, and we propagate tensor axis along factor K. Finally, we project the factor shardings to the dimension shardings, connected by the sharding rules. This one is the propagation results in the factor space, and after projection, we will obtain the shardings in the dimension space, where the RHS will got partitioned by partition along the first dimension, and the result will partition along the first dimension by the batch axis. And in this example, we do not discuss about this how we resolve conflicts, since we just defined the full hierarchy to resolve conflicts. We have defined 4 related passes. The first one is we first consider the user define the priority. If user define the specific priority, we are just following the user defined schedules to propagate shardings. For example, if you will consider the P0 shardings at first, and then P1 followed by P2 and P3. After, in the same user priority, we'll just follow the dimension priority and factor priority. For example, we consider the batch dimensions at first, and then followed by the other lower priority dimensions, such as reduction dimensions. In those operations, we propagate shardings along the non-constraint dimensions at first, and then the constraint dimensions. And the third step is how we resolve conflicts in a single priority. And in the base layer, which is the basic propagation, we do not resolve conflicts, and we just we depend on the upper 3 levels to resolve conflicts. And all these passes are just to form a hierarchy. For example, for each user priority, we just iterate all the dimension priorities, and for each dimension priorities, we iterate each aggressiveness in our propagation system. Okay, for the third component, which is not online at this time, and we are just making maybe it will be online in about August or September. There are just 2 key components. The first one is how we convert the abstraction of the reshard to the specific collective operations. For the background, we just have visualized several common collective operations in the mesh-based sharding representations. The first group is the dynamic size and altogether. On the left side, which is a partition tensor, which is a replicated tensor. On the right side, which is a partitioned tensor. We further partition this tensor along the first dimension along the sharding axis X. In that way, from left to right, which corresponds to the dynamic slice, we just further partition this tensor along a specific dimensions. From right to left, which is the inverse operation of the dynamic slice, which is an altogether, we just replicate something. We remove a sharding axis remove an axis from the sharding, which we make it replicated. And second one is all-to-all, which is the swapped axis between, of course, different dimensions. In this case, we move the sharding axis Y from the second dimension to the first dimension, which is an all-to-all, collective operation. Another one is collective permute, which is the reordering devices array. For example, from XY to the YX. This one is just response to a reordering of this device array. For example, in this one is just an exchange of a local exchange from device 1 to device 2. To swap data across these 2 devices, which corresponds to collective permute operations. In our reshards to collective operations passes, we just try this following operations group one by one, group by group. The first part, the group 1, which is the reduced tensor size, which is the dynamic size. Since we like to prefer the collective operations to be done in a smaller tensor size. And the second group is collective permute and all-to-all that maintains the tensor size. Finally, we'll try the altogether which will increase the tensor size. Here we have two examples. The first one is we have the collective permute and L2. From the source sharding to the target sharding, we first use the collective permute to reorder the sharding axis along the first dimension, and then with two adjacent L2, we just move the sharding axis to the corresponding dimensions. In the first L2, we move Z from dimension 1 to dimension 2, and in the second L2, we move X and Y from dimension 1 to dimension 0. In the second example, we have all these collective operations. We start from we start from this source sharding, and the target sharding is quite different from the source sharding. We just followed by the schedule we discussed above. The first step is trying to insert the dynamic slice to partition tensor as much as possible. In this case, we just partition the dimension 1 along X, since X doesn't occur in the source sharding. However, it appears in the target sharding. The second step is to use the collective permute to reorder the sharding axis in the same dimension. We reorder the shardings along the first dimension. The input is WZB, and after the reordering, we got the ZWB. With L2O, we just move the W and V from dimension 0 to dimension 1. Finally, with the altogether, we remove the sharding axis Z along the dimension 0. Shardy can just have this schedule and generate the collectives with the smaller tensor sizes, smaller tensor size. As a comparison, the JSVME has difficulty matching this reshard pattern, and it has to proceed with the last resort, which we call involuntary full remorphization. It will fully replicate tensor and then fully partition tensor. In this case, it will just have an expensive altogether to make the tensor fully replicated, and then using a dynamic slice to obtain the desired sharding in each device, which is quite inefficient in terms of both memory consumption and communications. And the second key component is how we resolve the conflicts in the partitioner. Is we insert explicit reshard. Here we have let's say after the propagation orders annotation, we have conflicts to be resolved by the partitioner. In this example, we have sharding axis A along 3 different dimensions, along 3 different factors in 3 tensors. LHS is partitioned along factor I, RHS is partitioned along factor K, and the result is partitioned along factor J. This one is just a standard dot operation. The input has the incompatible shardings. And we have 3 options. The first one is that we align them along factor J. Finally, we call it compatible shardings, since in this table, along each column, we have the same sharding axis. And to achieve that, we usually have 3 steps. The first one is to reshard the corresponding operands. In this example, we need to reshard the LHS, since we remove the sharding axis A from the factor I, which corresponds to an altogether. We reshard the LHS by an altogether. We reshard an RHS by an L2O. That's the first step, reshard the operands. And the second step is, now we have a compatible shardings along the operands. We can apply the dot operations with the local shape. And finally, we need to reshard the results to the desired sharding. In this example, the result also has already been in the desired sharding, so we do not need to reshard the result anymore. You can also align them along factor I in this example, we do not need to reshard LHS. We need to reshard RHS by the altogether, and then we can apply the dot operation. Finally, we need to apply an all-to-all to reshard the result or to achieve the desired shardings. Another option is that we align shardings along the contracted dimensions, along the factor k. In that case, which is in special case that we can keep the sharding axis A along the factor j, which is a reduced scatter pattern. In the first step, we need to reshard LHS through an all-to-all, and we do not need to reshard RHS. And we can apply a dot operation. Finally, we need to reshard the results with a dynamic size, and we can fuse the or reduce along the followed by the dot operation and the reshard for the result. Refuse the or reduce plus dynamic size into a reduced scatter. And all these three options have been considered in the Sharding explicit reshards. We have built a cost model to measure the cost of each option and select the best one. Actually, it depends on the size of this factor. For example, if the LHS non-contract dimension is very large, its I is much larger than the J, we will prefer the second option. If the K is much larger, we prefer the third option. So actually, it depends on it heavily depends on this size, the size of these factors. We have built this cost model to make decisions along these options for all these common and for all the operations in the stable. And finally, the comparison in the JS versus Shardy in the JAX, especially from the user's experience. First of all, as I mentioned in the very beginning, now you can experience Shardy directly in the JAX using by specifying the flag here, and this flag will just become true very soon. We expect to spot them in July. In the JAX, we have this. We will just lower the JAX name sharding and JAX matches into the corresponding Shardy dialect. For example, we lower the JAX name sharding into the Shardy shardings. We lower the JAX sharding constraint into the Shardy sharding constraint. Lower the JAX mesh into the Shardy meshes. An advantage of this sharding is that we will maintain the access name such that users can in the visualization in Debugger, users can find the original Shardy access names in the propagation results. Similarly, this one just how we just translate the corresponding named sharding into the sharding constraint in the sharding, and we are just take the input as sharding propagation. This one is just how we convert the JAX shard map into the corresponding Shardy manipulations into the in the Shardy. Above all, we just have almost one-to-one mapping with all the corresponding Shardy related APIs in JAX and in JAX. This section is just how we provide the usability and debugging tools for the users. For the Shardy representations and for the propagation and the partitioner, all of them can be visualized using the table we have demonstrated above. And this usability and debuggability just provide a much more visualization for these tables and for these propagation stages. This one is the basic philosophy, as I mentioned in the overview, that our target is trying to provide much more user control and transparency to our users. Similar to the JAX dump and XLA dump, we also provide the Shardy dumps. Users can just using this XLA flags to visualize the ML module and HR module processed by the Shardy after each key passes. We also integrate the Shardy results into the Model Explorer to provide better visualizations. The Model Explorer is a visualizer of the computation graph. It just visualizes how these operations are connected in this and their dependencies in the interactive UI tools. And we integrate the sharding into these tools. For example, in this tracing demo, we just have a simple JAX input, and then we will just lower them to this one. We'll just lower to the JAX to the MR module before propagation, and after propagation, we just have these shardings for each operation. With Model Explorer, we can just the sharding will just an attribute in this computation graph. For example, we have the shardings attached to each node, which is an operation. Users can also find the flow of sharding axis. For example, the data axis is propagated in this graph along these directions, as shown in this visualization. We also provide interactive debuggers to visualize how the sharding axes are propagated along these operations. For example, the blue arrow just demonstrated the propagation flow of the data axis, and the green arrow just demonstrated the propagation flow of the model axis. Another feature is that users can trace the origin of the specific shardings. For example, after propagation, we just find that a sharding is partitioned along several sharding axes, and we would like to know that why this tensor is partitioned along, why a tensor A is partitioned along along the data axis. What's the origin of this data axis? We provide the tools to trace back to the origins. For example, in this operation, we know that the data is from the input 0, and the data axis is from input 0, and it provides this the direction and the flow of the propagation of this sharding axis. Finally, we have discussed about the future work and the current status and the future work. The Shardy has already empowered Gemini and many internal workloads in Alphabet, and Shardy will just become the default partitioning system in JAX soon. We expect to flip the value. JAX will just use the Shardy by default in July. Afterwards, GXBMD will be deprecated following a 6-month application period, and we expect to just not maintain the GXBMD after by the end of this year. And in the second half of this year, we're just focusing on this PyTorch integration and integration with other frameworks and help migrate additional GSM users. Meanwhile, we'd like to just enhance its ability features, and especially based on the requirements from users. Also, the partitioner system, the single partitioner, as I mentioned above, the explicit reshards and the reshard collectives will be online to unlock performance gains, especially with the reshard to collective operations. We'll completely remove the expensive involuntary full rematerializations. Also, we have much more work in progress features which is under development. Yeah, that's all of this presentation, and I have this many backup slides, and I can just also delve into specific sections in details. So I just leave several time for the Q&A. Thank you.
How can we go from GSPMD annotated graph into a Shardy graph, and how can I enable that pass if it exists?
For JAX users, this line is the only change you need to make. You don't need to make any changes for the other Shardy annotations. So we provide a seamless migration for the JAX users.
Yeah.
also, say we want to export a PyTorch module to stable HLO, what is the recommended way to mark sharding? Is like you use XLA the mark sharding, or use the way you just mentioned, the JAX mark sharding when you trace the PyTorch module.
I'm not sure the current status of the PyTorch lowering to the JS spin shardings. I think we just the experience for the JAX that JAX previously lowered to the JS spin sharding, and we just make these changes that if this flag is true, we convert the JAX shardings to the corresponding Shardy APIs. That's all we need to do, and the other XLA passes can fully support the shardings at this time. So for the PyTorch, if it now supports the JS spin lowering, what we need to do is that we replace the lowering to the Shardy related APIs. For example, if we just once previously lowered to the HL sharding, we can now lower to the Shardy shardings. That's all we need.
So I had a follow up on that. So from PyTorch, we're able to get GSPMD annotated graph. Is there a pipeline or pass that exists that would convert these GSPMD into Shardy APIs? And can we call it outside of OpenXLA repo, like a link against Shardy or some other repo, and call that pass?
Shardy can be used either independently or integrated into the XLA. Shardy isn't just as an independent component. It takes a computation graph with partial annotations as input and propagate shardings throughout the graph and generate the graph with the sharding annotations throughout the graph. Also, you can also just insert explicit collective operations in this graph. So it can be a standalone component. Also, you can also use it as a free pipeline, for example, integrating in the JAX, in the XLA.
I see, but like my question is like, where is the logic that exists to convert a GSPMD annotated graph into a Shardy annotated graph?
We currently do not maintain this path. So historically we have this one, but it's now less maintained. We just at this time the Shardy input is directly from JAX or from the from the other frameworks. It's not from JSP annotation.
Yeah, so it's the tracing and visualization of the Shardy partition, the tool open source.
So the question is regarding this tracing?
Yeah, and also the visualization of Sharding propagation. So is that tool already open source?
Yes.
Is it like a standalone tool, or is it like part of XProp?
You can load Shardy dump into the model explorer, and it provides this interactive interface.
All right, great, thanks.
The big benefit for Shardy is like the user has more control, and like you mentioned, like user can specify like priority for propagation. Is this just the only part for user control, or are there other aspects that user can also have more flexibility on?
The priority is the most important one. Other than that, users can also define this constraining axis and dimensions. For example, if an axis can be used to partition this tensor, if a dimension is open or closed. Users here we define the sharding rules for the common operations. Users can also define their customized sharding rules for the specific operations, especially for their custom calls, custom kernels, and so on. As an example, we just recently supported the record dot operation which is a variant of the dot operation. If we would like to support it in the JXMD, it takes at least 6 months for us to fully support it in the whole pipeline. But with Shardy, we only need to define the sharding rules for the operations, and it takes us only 1 week.
Do you have any performance numbers for the performance gains you mentioned?
We do not have this public numbers, but in general, we have witnessed 3% to 5% improvement for the internal workloads, and with this explicit reshards and the reshard collectives, we expect to have 5 to 10% of improvements.
You mentioned the partitioner is going to be available in August/September. Where is this partitioner going to live, and will we be able to invoke it on our own dialect, or is it just for stable HLO?
It's dialect agnostic, so it can it's suitable. It's compatible with stable HLO at this time, and you can also apply the explicit reshards with your own dialect.
So sharding for JAX is, I believe it's already ready. And what about for OpenXLA? Is it like in the middle of development, or like it's also almost ready?
It's under development.
And it's like the expectation is like for the end, and by the end of the year, everything will go to Shardy, right?
We don't have the clear timeline at this time. We need to just make the evaluation on that. But I think we need when we have several preliminary results next quarter in Q3. Hopefully, we can fully support it by the end of the year.
Yeah, because you mentioned the deprecation will start at the end of the year. So I guess like it also includes like PyTorch, right? Or it's about JAX.
Yes.
And by saying assuming it's just to JAX, right? The deprecation is linked to JAX.
The deprecation is for both.
I saw.
Yeah, I think we will. We may take. We may not focus on this JFE maintenance next year and in the future, since we have noticed several inherent disadvantages in this GSP system, and we like to just focus on the Shardy maintenance and development.
Yeah. So what's the status of NPMD support? I think the keynote someone mentioned like Shardy supports NPMD.
Yes. But that one is maintained by another team. It's migrated from PodIR, as I mentioned in this slide. Yeah, the PodIR has both SPMD partitioning and MPMD partitioning, and now they have also migrated the MPMD part into the Shardy. But that's out of the scope of this presentation. Yeah, and MPMD will be public very soon. I think it will be available in July or August.
I see. Thanks.
Okay.
Is there a way to convert Shardy collectives into stable HLO collectives?
Yeah, we provide the corresponding round trip passes.
Thank you, Zhang, for the presentation, and thank you everyone for joining the talk.
Thank you.